Hello everyone, welcome back to my channel. Today I'm going to be solving a question about temperature distribution in a cylinder. Now in this question, we have a cylinder over here in which we have also specified as part of the question that the temperature changes only with respect to the axial direction or the z direction over here, and it does not change with respect to the r direction over here. Maybe because I could say because of the Biot number, or in other simple words, like the r direction is too small compared to the length of the cylinder. I could make that assumption. And then heat is being applied in two different forms. First of all, heat is being added from the lateral face of the cylinder, and secondly, heat is being lost from the end caps of the cylinder over here, we can see. And this heat is being lost through convection to the air, and the air is at the ambient temperature of 20 degrees C, and the heat transfer coefficient is H, and the heat flux applied from the lateral side of the cylinder is Q. Now let me make a heat conservation equation based on the above inputs which I given in the question. Now, as we talked about that the heat changes only in the z direction, I am going to choose a differential control volume in the z direction over here. So what this basically means is I cut a slice out of my cylinder of thickness, let's say delta z. So this is my thickness delta C. This is the slice I cut out of my cylinder. Now this slice is going to have a surface now this slide is going to be of this area is going to be AC, the control area, and then the thickness is going to be delta Z. Okay. And since my temperature is only changing with respect to the Z direction, so the temperature in all of this AC in the Z direction from top till bottom is going to be the same. It's only going to change in this direction, okay? Not in the up or down direction. Now let me make a heat equation on this. So I make the heat equation on the basis of my control volume over here. So I can say that the rate of heat in my control volume equals the rate of heat out of my control volume. So I can denote this by the flux, which is QZ over here. And let's say a flux of QZ is applied at Z, okay, at Z is equals to Z, and then the flux leaves at, and then I'm going to evaluate this at Z plus delta Z. Okay, so this is my input over here at Z. The flux is entering at Z and it leaves at Z plus delta Z. Okay, now this is my flux, and what is basically flux? Flux is equals to the heat applied divided by the area into time. So if I'm trying to find the rate, I'm just going to multiply the flux by area. So I apply this flux, and then I am going to multiply by my control area AC, and then I evaluate this at Z, and then because this is the heat entered, and then I subtract this at Z plus delta Z. Okay, because of my system, it starts at Z and it ends at Z plus delta Z. Now this isn't the only thing that's happening. I am also applying a heat on the lateral surface. So on this surface I'm also applying a heat, but for that flux at the flux Q, but for that flux the area is not this. I'm not applying the heat in this direction. No, that's not the case. I'm applying the heat in this direction. Okay. Now for this, the direction in which the heat is applied, the perpendicular surface area is going to be different. And that area is highlighted in green over here. Now when I open this up, this becomes a rectangle with thickness delta Z and like the length of 2 pi r. Okay, because this is just the perimeter of the circle. Now I can then multiply these two and denote the area as pi d delta Z. So this becomes my heat equation. Now just to clean everything up a bit, I am going to divide my heat equation by delta Z, and then I am going to apply the limit as Z approaches 0. Okay, now when I apply the when I divide this by delta Z, as we can see over here, these two get cancelled, okay, and I obtain q pi d. And when I divide these both by delta Z and take the limit as Z is equals to 0, I obtain this term, which is the simple definition of a derivative, and I obtain the negative sign because Z plus delta Z is subtracted from this. Okay, normally this should come here and this should come here for it to be positive. Anyway, so I obtain this, because of the definition of a derivative. Now moving on, since my heat equation, this is my heat equation now, since this is in terms of the flux, I kind of want to make it into more of a friendlier quantity, something which I can measure. So I'm going to relate the temperature to the flux. I'm going to apply Fourier's law. So the heat flux in Q in the z direction is equals to K, thermoconductivity constant, multiplied by the temperature gradient in the z direction. Now I'm going to apply this formula over here. Okay, since K and AC are constant, I am going to take them out of the bracket and they come here on the other side. Now I have a second order separable differential equation. I can integrate them. This dz goes to this side, okay, and then I integrate them. Now when I integrate this with respect to z, I get c1 constant, and then since these two get cancelled, I just get dt over dz. Now I'm going to integrate them again, and this dz again comes here, and I integrate this again, then I integrate this again, and I get t. Now we have two constants over here, c1, c, and c2. Now this is my final equation, but unfortunately it has two constants over here, c1 and c2, and we need to evaluate them. Now I'm going to use my boundary conditions over here to evaluate these two constants, c1 and c2. Okay, my boundary conditions, let me just go back and see what do I have for my boundary conditions. So I have my two end faces at z is equals to 0 and at z is equals to L, and over here we have air at the ambient temperature of 20 degrees Celsius, and then the heat transfer coefficient as Z. So I can say that all of the heat escaping my cylinder at z is equals to L is equals to the heat transferred into the air by conduction. So the heat lost by heat is equals to the, like I can say that the heat lost by conduction over here is going to equal the heat transfer to the air by convection. Okay, now let me just translate back that into my boundary conditions. Now, what is the heat transferred by conduction? We applied the Fourier's law. It's going to be Q, this is the flux QZ, and I'm going to multiply the flux by area AC, so I get the heat transferred by conduction. I then apply the Fourier's law over here to define the flux, and then since this is at z is equals to 0, I evaluate this entire expression at z is equals to 0. And then what is the heat transferred by conduction over here? I am going to write Newton's law of cooling, which is just the heat transfer coefficient H multiplied by the area and then by the temperature difference. So this is the expression that I obtain at z is equals to 0. Similarly, I obtain the same expression at z is equals to L over here. The only difference is this T is going to be evaluated at L, and this expression dt over dz is going to be evaluated at z is equals to L. This is the only difference between these two boundary conditions. Okay, moving on, I'm going to apply my boundary condition 1 over here, and let me just write it in a much better way. Okay, let me just write them in a much better way. Now when I evaluated this at z is equals to 0, I have the expression for dt over dz at z is equals to 0, and since this cancels out, I am only left with c1 over here. Now I also have the expression for my t at z is equals to 0. It involves two z terms and they also cancel to 0, so I get this t at z is equals to 0 is equals to c2. Now I insert everything back into the boundary condition 1. We see that the ACs get cancelled out, and then we get that the ACs get cancelled out, and then what do we have? We have this expression over here, and instead of T, I'm going to insert C2, and instead of dt over dc, I'm going to insert C1 as I evaluated over here. Now I obtain a more cleaner form of my equation over here, and this is something I can work with. Okay, now I apply the boundary condition 2. Similarly, in this expression, I substitute the z for L. Okay, and this is the expression that I obtain. And same for the t, I substitute Z for L, and this is a more complicated expression that I obtain. Now again, I am going to input this into my boundary condition over here. The ACs get cancelled over here. Then I'm going to apply this back into my second boundary condition over here. Okay, and over here, once I have inserted these both, so this becomes my boundary condition 2, and this becomes the first one is my boundary condition 1, the cleaner versions of it. Now I have two equations and I have two constants, C1 and C2. I'm just going to solve them simultaneously until I get my two integration constants. And as I can see over here, C1 is a more involved term. Like it is getting more multiplied, it's a little bit more tied up than C2. So it's easier to replace C2 instead of C1. So I'm just going to make C2 the subject of the formula and I'm going to insert it into C1. Okay, now I transform equation 1 over here to this. Okay, now once I've transformed it, I insert this in the place of C2 over here. Now right off the bat, I can see that the temperature at infinity is getting cancelled. Okay, so this temperature at infinity, it just came from the Newton's law of cooling, like which we talked about in the boundary condition 1. Okay, so this simply, I can see that this gets cancelled. Now I like to call it algebraic juggling. I picked that term up from a textbook, quite funny if you ask me. I like to perform a little bit of algebraic juggling because we have this one term C1 over here. I am just going to isolate it and try to make it the subject of the formula. I've included some intermediate steps so the process becomes a little bit easier for you guys, and I'm just going to walk you guys through what I did. Now what I did is, first of all, I multiplied this K, I opened this bracket, and then I opened this bracket for H. Okay, once I opened these brackets, I could see that the K's got cancelled, and once I opened the bracket for H, I could see that these two terms get cancelled, which automatically reduced the load of my equation and made it less heavier. Now, when I obtained this quantity, I just shifted C1 on one side and I divided the entire thing by LH. Then I did more cancellation. I can see that these L's get cancelled over here and some of these H's get cancelled over here. And my equation just turns into this tiny little clean quantity with like very few terms. And this is my final equation for C1. Now, our work hasn't ended here. We go back and we saw that C2 was in terms of C1. So I'm just going to insert the value of C1 back into C2. Once again, we obtain a kind of a heavy equation, but I just like breaking it down. And I am going to break it down by first removing this from the denominator and then dividing each term individually. Now, when I divide each term individually, what I can do is I can take this term as common and I obtain this simple thing, this simple equation, or like it's easier to look at, it's easier to evaluate. And I isolate this, and then I have my expression in terms of C2, and I have an expression for C1. And I can put these two both in my final equation T over here, and this is my final temperature distribution. Now, let me know what you guys thought of my video, and I hope it helps you guys, and also let me know if this was too long. Please do comment on my teaching style, and that's all I have for you guys this week. Thanks for watching.